Sounds good. So we're ready to get started? Awesome. So thanks everybody for coming after lunch. I know everybody's a little sleepy. Hopefully you got your coffee and everything. I'm really excited to be talking to you guys. I'm Mark Marin. I'm from Microsoft Research. I'm going to be talking today about some work that I've done and done with colleagues on time travel diagnostics and building actionable insights sort of on top of this going forward. And since this is Splash I, I'm also going to take a little time to talk about some of my experiences in this project and in general, collaborating with industry, both industry as in our product group partners at Microsoft, but also open source community members and sort of collaborations in that area. So today, we got some of them. I've done a lot of work with the Chakra JavaScript engine team on this at Microsoft, with the Visual Studio Code IDE team, also at Microsoft. And then, I was talking about sort of this open source, the Node.js Diagnostics working group. Have been some great people to work with. So I just wanted to, give a shout out to them before we get going too far. So I mentioned a lot of JavaScript people there. And kind of like the question is, well, why are we interested in JavaScript? Or why did we focus on this project in JavaScript? Well, JavaScript just seems to be appearing more and more places. It's more and more popular. People write tons of things in JavaScript, so it's just a ubiquitous language. But even more than that, if you look going forward, people aren't writing things necessarily in JavaScript anymore. Maybe they're using TypeScript, but that still transpiles down to JavaScript or Flow or ReasonML or React for your new phone apps. They're still part of a JavaScript ecosystem, and more applications are using these enhanced frameworks, but it still boils down to JavaScript. And if you look, JavaScript has escaped the web. It's not just in a browser anymore. People are using it to write desktop applications with things like React and the Atom stuff, server and IoT with Node.js. So it's just, now it's powering a whole class of applications. And so I mentioned Node, everybody's favorite. I don't know how familiar you are with everybody is with this. I'll talk about it a little bit, but you can basically think about it as a runtime environment that hosts a JavaScript engine and provides a bunch of functionality that makes it really easy to write web servers. So it provides a file system API, provides an HTTP server API, and it's extensible. So if you need some other native bits to hook up some functionality to your JavaScript code, you can plumb that in as well. So as I mentioned, we are interested in Node.js, and one of the things that people really do with that, and we like it, is for putting together simple server applications for like line of business or web apps or this sort of thing. I write some code, I deploy it to a cloud environment, whether it's a server I run or it's something like Azure or AWS in a Docker container. It's very easy to set up some code, solve a problem, stick it in the cloud, it chugs along very happily. And it's great, you put the code up there, and then eventually things will go wrong with it because it's code, and we all write buggy code. And so sort of what we have here is an idea of a workflow that comes up when you're a developer and you run into some problem. So you put your code in the web, and eventually you get an alert that something has gone wrong. Maybe it's somebody emails you that it's broken, you notice the server's not responding, you've paid money for a service that actually monitors the health of your application, and it pops up a flag on the dashboard, whatever. From there, you say, okay, I have a problem. I start investigating it. I look at, did another service go down? Was there a call stack trace? I sort of try and figure out what is relevant to this error. I eventually figure out how to do a local reproduction on my desktop so I can debug it. I dig around for a while. I figure out the root cause of the bug. I come up with a way to fix it. I take that test. I put it into my, unit test, PR, CI/CD pipeline. It churns around for a while. Everything passes. And then I click deploy, and I fix the bug, right? So this is sort of the general workflow that developers go through in this cloud-based environment today. What's interesting is that if you imagine a simple bug, I forgot 2 parentheses. Each of these steps is pretty fast. Like, I'll see the problem. I'll be like, oh yeah, that's the wrong line in my exception call stack trace. I'll see immediately where the bug is. So each of these steps is 5-10 minutes. But to get from the alert to the actual deployed fix is like a half hour of your time. No step is very hard, but it just burns time. And so if you're a developer and you come in the morning and you have 4 bugs in your to-do list, you're not getting anything done before lunch, right? So these kinds of small bugs become very parasitic loss on productive developer time. And they're just demoralizing. Nobody likes to spend half their day fixing 4 stupid bugs and not getting anything exciting done. More problematic is when I have complex bugs. Maybe the investigation of the repo, they're non-deterministic. It only happens every so often. It can take hours or days to track down and fix these bugs. And the whole time that bug is not fixed, it can be impacting customers, and you're having unhappy people. So nobody likes that. And even worse, every team I've talked to, we have 1 or 2 bugs that we know they're there. We know they pop up, but they just do it so intermittently or so randomly. They've sat open for 6 months and nobody quite knows how to track this one down. We doubt anybody's going to be able to do it anytime soon, and so it's just sitting there annoying us and customers complain. So we hate all that. So really what we'd like to do is we'd like to speed up this process, eliminate some of these pain points, and allow developers to focus on what they care about, which is writing code that solves a problem, not mucking around with their flow and fixing bugs. So what is the state of the art today? Well, pretty much today, there's a lot of support for what's called application monitoring. And so with these APM solutions, they provide a comprehensive set of monitoring and alerting tools for your application. So they'll tell you, is your application alive? How many requests is it responding to a second? How long does each request take? What's the 95 percentile latency? How much memory are you using? And if any of these things goes out of whack or something strange happens, it'll throw a flag up. It'll pull logs back from the application. It'll give you a call stack. It'll try and give you some other stuff to help you investigate and narrow down and start on this process. But as you can see, it's really not solving a lot of the actual more complex stuff. So the project that we worked on is how do you go about addressing a lot of this expensive investigation, reproduction, and debugging stuff. So I'm going to show a quick demo here of kind of the scenario we have come up with and the tool we actually deployed and built in collaboration with our product group partners and some the Node.js open source folks. So I'm going to ask a quick question because how many people here are familiar with Visual Studio Code? Okay, that's pretty good. I'm pretty happy with that. So this is Visual Studio Code. It is a lightweight cross-platform, so it runs on Mac, Linux, and Windows, the other important one. And it provides a really simple, lightweight editor, code completion, highlighting, Git integration, and sort of scripting environment for a lot of development. It comes with support out of the box for TypeScript, C#, but you have add-ins for C++, Python, Java, whatever you like. So this is actually a really nice, easy development environment. It's become, yes?
Can you kill the lights on the screen there? It's a lot of glare.
Okay, so you can switch the door. So anyway, while we're doing that, okay, hey, there we go. The eye exam got easier. So this is a very nice thing. It's very popular. A lot of people are using it. So I can't recommend it enough. And interestingly enough, it's built on Node.js. So as I was saying, JavaScript is everywhere, Node is everywhere. Well, here it is running my IDE. But getting back on the topic at hand, so here's a sort of a representative Node application for you. We've set it up where maybe I had some files I needed to share with everybody on my team. I wrote a Node server that allows me to browse directories and preview files in a browser window served up by this application. So I can come over here, and I will just launch Node serving this application up. I can come to my browser window, refresh, and as you see, I have some files over here in directories on the left. I can click on them, I can see some contents, and as a user, I'm clicking around. I clicked on helloworld.js, and it comes back and says, oh, there was a request error, file was not found, and I included a timestamp that ends in 111. So I might, walk over to my colleague who wrote this and say, hey, I was clicking around, there was this bug, and he'd say, okay, today, what do? Well, I open up my editor, I scroll around, and I see, okay, here's that file not found error message, and I'll look around, sort of the call stack, I'll see it happened in read file. And in Node.js, everything is callback oriented. So read file takes a file path, and then it takes a function, which takes 2 arguments, either an error, if there was some problem reading the file, or data, which is the contents of the file. And so as you can see, well, an error occurred, and I dropped right here into this error case, and I just reported the error. But I don't know what the error was. I don't have a lot of information, so I don't have a lot to go on and try and reproduce this bug. But since I was running this application in record mode, I actually wrote out an error trace that encapsulates everything you need to totally reproduce everything leading up to that particular bug. And here in my IDE, I can just refresh the set of traces I have. I'll see I have this new trace. I can load it for debugging, so it'll take that trace, it'll restart it, it'll start executing it, and I'll break right here down in some emit trace code, but if I go up to call stack a little bit, I'll see it's broke exactly here on this line where I had the bug. And if I look at the file path variable, it's hello world.js, which was the file I was looking at. And in fact, if I look at the timestamp variable, it's that 111 timestamp. So this is exactly what happened when that error occurred in practice. I'm doing this on my local machine because I don't trust networks and conferences, but you can imagine even if it was on a server up in the cloud somewhere, we'd be recording everything as it happened there. So not only do we allow you to basically eliminate that whole need to investigate or figure out how to reproduce your bug, all you have to do is launch the trace. Reproduction is done. But we can actually step back in time and see other things that were happening in that trace. So one of the problems with this callback model is, since I'm in this callback, any local variables that were not captured before this callback was put into the work list and this function was returned from, I can inspect. So here I can see file path because it was captured here, but I might want to look at the root directory, but that's no longer on the call stack, so the debugger can't show it. So what I can do is I can set a breakpoint back in time when I was actually setting up this callback. I can use this reverse execute functionality to execute back in time, and you can see file path is still hello world.js. But now I can inspect all of these variables that were previously lost. And not just like at the root level, I can drill down into any sort of compound structure that I want. So any value that was inspectable at runtime, if I magically attach the debugger at the right point, is inspectable here.
Are you stepping backwards, or did you jump back to some point? How did you find that point?
I can't give away the match. No, I'm going to go to that next immediately. So this is the kind of experience we wanted to build, right? That we thought was really exciting, and we got a lot of, this is not the first time.
I'm not asking you how you implement it. I'm asking you what you're doing in the UI.
Oh, what are we doing in the UI?
What did you do? You said, I set a breakpoint back in time. What does that look like? I set breakpoints at places, not in times.
Yeah, so I can step back now. So I can, file request time here, it's a value, I can step back.
So it's undefined. Reverse execute.
Reverse execute, yeah. I can step forward, I can keep stepping back out of this function, up to call stack, through all sorts of whatever.
Okay.
Yep. So this is the experience we wanted to build, and we iterated a lot with our product group partners on what this should look like and how this would actually be useful to developers. But let me talk about now how we actually went about building this and what we think about going forward. All right, so there we go. Okay, so as I mentioned, now since we have these time travel traces, you don't need to worry about investigation and reproduction anymore. That's fully gathered for you. Further, we've not automated debugging, but now you can step back in time, so you can sort of easily trace back to the origin of an error, step by step, rather than having to sort of iterate, set breakpoints, and guess around. And of course, you can sort of use these traces. If you have a fix, you can run it again, make sure you don't see the same bug, and do a little validation if you have in the testing PR stage. So key question, well, how does time travel work? Right, so we don't actually reverse program execution. When I step back, I didn't somehow undo the effect of each statement. Instead, we use sort of what's known as record replay with snapshots. This is a fairly well-known technique. Several other people have implemented similar systems. And then what we do is during regular execution, we'll log not every statement that's executed in its effect, but only the effects that are non-deterministic. So if you read the current time or you read the contents of a file. And we'll take snapshots every so often of the entire program state so that if we want to go back in time, what we're going to do is we're going to jump back, restore that past state, and start executing the code. And whenever we need a non-deterministic value, we'll just read it from the log and we'll interpolate between any two snapshots. So let me just walk through a simple example to give some intuition. So suppose my program counter is here at this function, And at this point, I'm going to take a snapshot of the entire program state, which I have down here. It's very simple. It's one variable with two fields, x is 5 and y is 3. And I'll just copy that over into some serialized snapshot representation. Then I'll just keep executing the code. I'll see, I'm going to do the assignment to point as x. I'm going to read math.random. That's a non-deterministic input. So I'll just remember whatever value random returns for this particular call. So it's 0.5. I'll update x as usual, so it becomes 1. I'll move to the next statement. This is fully deterministic, so I don't need to log anything. I'll just update y to 1, and I'll move to the return statement. Now let's suppose I want to step back in time, and I'm here at this return. So what's the first thing I do? Well, I'll just reset the program counter back to the place where I took the last snapshot. I'll take that snapshot state. I'll just overwrite whatever the current state is with what I had at that snapshot point, and I'll start executing again. And now I get here, I see math.random, and I don't want to generate a new random number. I want the behavior to be exactly the same. So I'll read whatever I recorded from the log, and I'll return that as the result of math.random. So it'll be 0.5 again. I'll update x to 1 just as before. I'll take a step to the next statement, and I'll know this is the statement that immediately preceded the one I was at, so I'll stop there, and I've successfully stepped back in time, sort of in a roundabout way, looping around. Yeah.
Right, so this is similar to, it's similar to what sorry, 3D graphics APIs do, for debugging, wherein they trace the method calls, for instance, in OpenGL, and then they replay them back. Is this kind of what you're doing? Is this a similar approach?
Yes.
You just record the non-deterministic ones and then you replay them.
Yes, and it's very interesting. People use this for, I don't know if you're familiar with like the React rendering framework, where you say I have a state object, and everything that I generate for the GUI is going to be deterministic, so I can do time travel by just resetting the state object, and then it will render the same GUI. So people use a lot of the similar, like if we control determinism, we can actually sort of bake time motion. Yes, definitely. So
if all of your state is in an object, including the program counter, I know how to do that.
yeah,
But in general, I don't know how to reset the PC in a JavaScript program, nor do I know how to overwrite the state.
yes. And that is the trick. So we got to do two things. We got to do the record replay, right, in a deterministic way, which is, is challenging. We have to take snapshots, and we need to be able to capture all of the state. We need to persist it in a stable way and be able to restore it entirely. And the third thing, which is very important, is especially if I want to run this on production workloads in the cloud that users are interacting with, I have to do this very efficiently, because nobody's going to be happy if they're like, oh yeah, I'll do some recording, but it'll take 3 times as long to respond to a user request, and everybody will quit using my service and hate, right? So we have to figure out how to do this fast. So to explain that, let me just take you for a quick walk through how Node is set up. So JavaScript is kind of a funny language. It has no built-in notion of how to do I/O of almost any sort, right? It only knows sort of how to execute JavaScript code. And it depends on a host to provide it with APIs to do any sort of interaction with the outside world. So in the browser, it gives you like XHR requests. Node gives you a much richer surface where it gives you file I/O, it gives you network sockets, it gives you a console and this sort of stuff. But so you have a host which is going to provide a bunch of I/O functionality. You have the Chakra core JavaScript engine, which is going to talk across this JSRT embedder API. And the application is actually going to sit on top of the Chakra core JavaScript engine, right? So if you look at this diagram, and of course this all sits on the operating system, you can imagine that we could record non-determinism at a number of levels. So one option is, we'll just say, well, I'm going to record everything that the user space does with the operating system, and I'll replay that. So I'll replay the entirety of this process as it executes. That's a little heavyweight because we really only care about just what the JavaScript application is doing. I don't care about the GC or the network card or anything like that, right? We can sort of come up a little bit higher level and sort of record like the VM level, not the entire operating system, but just this particular process. But again, if we do that, we're recording like, allocations and, network packets and all that sort of stuff. Instead, what we do is we have this very nice boundary of this embedder API, a JSRT. So we're just going to record only non-deterministic events that happen at this JSRT API plus a couple of internal calls that Chakra makes to the operating system around that. So what are the benefits of this? Well, the JSRT API is like 150 methods or something versus a huge number of Min32 APIs or a large number of sort of complex POSIX APIs. The types are simple. They're either pointers or numbers or strings, so it's really easy and efficient to record them. And it simplifies record replay a lot. So we don't need identical binaries or builds of operating systems. I can actually take a recording from Linux and I can replay it on Mac OS, right? I don't care as long as the JavaScript engines are sending their equivalent. So just, to give an example, it's not really hard, but so suppose I have this JSRT API that's create string, it takes in some characters and a count, does some code. Well, all I'm going to do is I'm going to add a call that says, hey, log the creation of the string if recording is enabled, and in log creation of the string, I do the obvious thing. I just dump pointer allocate a buffer for the contents of the string, and then I mem copy it over there. Then for replay, well, all I'm going to do is when I get to that in the point in the log where I'm supposed to create a string, I just go look at my log, look for the current string that I'm supposed to create, allocate it for the Chakra JavaScript engine, and pass it back in. And it looks like it's happily interacting with the rest of the world, just as it did the first time. Snapshotting, similar sort of setup. If you look at a lot of previous work, they've used, the classic way to do a snapshot is just, I'm going to do a process copy on write. So I'm going to capture everything that's going on in Node, in the JavaScript engine, and the user application. And this has some problems. Again, I'm going to, take a dependency on the specific binary version of Node. It's not going to be sort of transposable anymore. But also, if you look at a JavaScript application or a Node application, there's a lot of space that's taken up by temporary download buffers, decoded JavaScript into bytecode, JITted code, GC free space, all this sort of stuff that I don't care about and I don't want to have to copy as part of the snapshot. Instead, all I want to do is just copy the JavaScript heap state, and that's all I care about preserving, right? So that's what we're going to do. We're going to take a managed snapshot of just the application state, not the entire process state. And again, what are the benefits? Well, in JavaScript, I can't address introspect. So if I'm just taking the JavaScript objects, I don't need to worry about being bit precise. I don't need to worry about preserving pointer locality or anything like that. And the key thing for us is, if we think, what is a snapshot of the application state? Well, it's all of the local variables, right? I need those. And then I need anything the application can access, which would be any pointers that are reachable from local variables, transitively out through all the objects and the values. I need to find all of those, and then I need to copy them to some serialized buffer. Now, this looks exactly like a GC, right? I'm going to find the roots, I'm going to mark the live objects, and then if I'm a copy collector, I'll copy them off somewhere else. So this means that instead of doing some bunch of extra work for the process snapshot and managing all of that, we can take a snapshot of the application state just by doing the moral equivalent of one extra GC. And in a language like Chakra, you're already paying the cost for the GC. So an extra GC every couple seconds is basically free to you. So this means we can do recording and snapshots at very, very low overhead. Another great thing about this is, rather than taking 30 megabytes, 40 megabytes, 100 megabytes of process, the live GC heap is much smaller, 10 megabytes. And it's very amenable to compression. So these snapshots can get very, very small.
Quick question. So do you do any sort of diffing between those snapshots?
In theory, we could. In practice, we have not. It's one of those things. It adds complexity, and so we sort of built the simple version first, and the performance has been good enough where we haven't had any issues coming up with it. I think we'll certainly want to do something like that in the future, but it hasn't become an issue just yet. So, again, just as an example, here's our current JavaScript heap state. We're going to identify the actual live objects, and then we're just going to copy those off into some serialized format that we can inflate from. So a little bit on the implementation. The majority of the changes that we made are in Chakra Core, which is Microsoft's open source JavaScript engine, so this is all publicly available. It's the same engine that powers the Edge browser. It has an interpreter, JIT, concurrent parallel implementation of GC, runs on Windows, Mac, and Linux. So this is all publicly available. You can build it on whatever platform you like. We had to make some changes to Node, and there's a special fork that runs Node with Chakra Core instead of V8 in Node Chakra Core, also open source. And one of the great things in this is the Chakra engine has collaborated heavily with the Node Foundation. So this is an official Node Foundation supported project, part of the repository. You can grab it from their downloads page. So this is available to a lot of people. And as I showed earlier, Visual Studio Code is great. It's very extensible. We actually were able to make all our changes to get debugger support, I think with 1 or 2 very small changes to their main code base. But now anybody can add time travel debugging for any runtime that they build a debugger for in Visual Studio Code UI. And then we just published an extension that's actually downloadable from the Visual Studio Code extension marketplace. So, a fair bit of work here, but we're able to spin up everything else without too much effort. So the key thing then is, well, we said performance is important. So what kind of performance do we see? And when we talked with developers on how they could use this in their workflow and what we could do to best support them, really what we heard is, this is sort of a Node philosophy. I can scale out infinitely. So if I need to get 10% more servers, that's not a problem. But it is critical that when a user sends a request to my website, they get back a response within an acceptable amount of time. So we don't want to add any performance overhead to the critical path, which is latency and responses, but we can pay more overhead generally if we can spread that out across scaling servers. So increasing response time by 2x was not okay, right? But if I have to decrease the number of, the capacity of each server, that's all right. I can just get a few more servers and spread out the work a little further. So with that in mind, we made some choices, and if you run the benchmarks on sort of compute-intensive applications like Octane, which is a very, it's a compute-intensive JavaScript benchmark. Might not be the most representative of real workloads, but it is very focused on compute. You see a slowdown of less than 5% and about a 2x memory increase in the process size. If you look at a sort of low utilization, line of business style app like the file server we had, slowdown is less than 5%. I mean, in practice, it's probably more towards 0% on a low utilization server. And again, memory increase is about 2x. We also did some experiments with much larger applications. So this would be a large internal server that actually, loads on more than 100 megabytes of JavaScript code, and you run their throw their load tester against it, which is really just pounding it with requests. You see a slowdown, maybe getting up to about 20%, and maybe about a 3x increase in memory footprint. But for our somewhat unoptimized version, this was great, and 10 to 20% is survivable. If you're doing just flying rings, maybe not every instance of the server you have running. So we were really excited with this. We were like, hey, this actually provides a lot of value to developers. This simplifies sort of our conceptual model of how you go about fixing bugs. It meets all our performance requirements. It's actually practical to use in practice. But, all of these discussions with the developers, it really got me thinking and got me excited about we can do, a lot more than just time travel debugging. I mean, I get excited about time travel debugging. That's very cool. But I think it's just a first step. It's really an enabler for other stuff. And so the question is, well, I can run this recording at 5%, maybe 10% overhead. And it's great, you have a crash, I take a trace, I allow you to download it and start debugging it. But there's no reason why I only need to record one failing execution for you to debug. I can record successful executions too. I can record lots of failing executions. I can store them, they're only about, often 10 megabytes, 20 megabytes each. I can store a bunch of these. And when I replay them, since I'm not tied to a bit precise replay mechanism, I could replay them and I could turn on extra tracing that, I could record every memory allocation what line it was allocated on. I can do lots of other stuff in this replay phase, and I can replay it as many times as I want, turning on more and less information as I narrow in on something that interests me, right? Beyond that, if you look at how modern CI, continuous integration, continuous deployment pipelines are set up, there's a ton of other metadata that's just really interesting. So I have all the commits that happen to a project before a failing trace. I have bug metadata from other things that were fixed. I have telemetry, I have log data coming through, test assets, all sorts of great stuff. So there's this incredibly data-rich environment that I'm now sitting in. And the question is, well, what can I do in this new data-rich world, right? So that's the exciting area we are today, and we're just starting to investigate this. So I'm going to do a bit of aggressive hand waving and say, you know, we still have debugging. That can still be really expensive. Fixing, we haven't helped the developer with at all. So what can we do there? Well, we have all these traces. We have all this metadata with them. How can we use, you know, either existing, yes?
30 minutes.
Oh, 30 minutes, thank you. How can we use either existing programming language, you know, technologies, just, you know, slicing, some of these trace analysis tools, or some of the recent developments in machine learning to go and say, hey, if you have a simple bug, can we just find the actual point that that bug is at? And can we automatically pinpoint that for you? Or if we can't, if it's a complex bug, we can't do this for every bug, can we at least automate a bunch of the rote work you need to do? There's no reason you should have to step back 30 times. If we can just say, oh, you want to know where the value in this variable came from? We'll just drop you right back there. So you can focus your energy on the intellectually challenging part of the grunt work. So I think we have a great opportunity to improve the debugging process. But then also, you know, fixing and testing various bugs as they come through, right? In particular, there's just a lot of work that's coming out in terms of program synthesis and using deep learning in program synthesis that I think will enable us to automate, again, simple bugs, the fixing of, you know, I missed a parentheses, I should have put an if condition somewhere, or at least helping accelerate the process of coming up with a fix in the case of more complex bugs. So this is a little hand waving, but let me give you a sort of a concrete example of some developments that I think are interesting, and in particular the fact that they're happening in collaboration with industrial partners or, you know, industrial engagement. So program synthesis for repair is, you know, a fairly vibrant topic. There's a lot of work in it. One thing that I think is really exciting recently is sort of some developments in what I'm going to call natural program synthesis. And so this isn't just, I want to come up with a program that satisfies some spec, but I want to come up with a program that satisfies some spec conditioned on some notion of what natural or human written source code looks like. And why would I care about this? Well, if all my spec is only a few tests, right, it's kind of easy to generate a solution that fixes the bug in case of those two tests. I just hard code the constants that return the right answer for those tests. But if I have a notion of naturalness, that's very unnatural code. So naturalness provides a very nice proxy for generalizability of the solution. The other thing is, and this really became apparent to me when we were talking with developers about their workflow, and it was, as a developer, if I check code into a repository, I'm taking responsibility for that code, and if it breaks, you know, my team is going to come look at me and say, you checked in broken code, right? And that doesn't look good on me. So if a machine generates a patch, even if it's perfectly correct, if I can't look at it and feel confident that I'm going to sign off on that and take responsibility for it, I'm not going to accept that patch. Even if it's good, even if it would make my life better, I'm not going to do that unless I have confidence. And so if I can produce code that is natural, that, you know, is easily understandable by a developer, and they can feel confident in what it does, they can quickly grok its meaning, and they can say, yeah, I'm going to sign off on this, I'm comfortable with this. That is actually a huge part of coming up with a good solution. And I want to point out two projects, and why I said I was very excited about this. So Mark Harmon at Facebook Labs has been working on Sapiens, an automated testing tool, and has done some work with this system called Sapiens SapFix, which is actually generating fixes for simple bugs and committing them and getting them checked into the Facebook code base. So this is very cool that actually getting some experience generating automated patches in an industrial setting. The other one, which I thought was a lot of fun, Martin had this Repairinator project where they would watch some popular open source repositories, keep an eye out for a check-in that created a build break, and then they would attempt to automatically synthesize a patch that fixed that build break and open a PR and see how many of these got accepted as that they submitted. And they actually did get a fair number of patches accepted and submitted. And then, so sort of an interesting Turing test for pull requests, I guess, right? Can you tell if this is a human or a bot that sent this PR to your code repo, and are you willing to check it in? So this is very cool. So with that in mind, I said there's some hand-wavy stuff, and it's very exciting to me. But I think like this previous example, it requires both some fundamental research, as in understanding and developing techniques for modeling natural source code, which was definitely something that came from sort of this blue sky, deep neural nets type research, and collaboration with practitioners. So understanding how this would actually work when you're doing this Turing test for PRs. And so I want to relate this back a little bit to, I described this project that we did with time travel debugging. I said we collaborated on that. Well, what did that look like? What was sort of my takeaways from this experience? Well, a lot of it comes from, we need to do foundational research, right? We need to go try and do crazy things. We started out and we said, hey, we'd like to do really fast snapshots by piggybacking on the GC. Does that work? I don't know. Let's try it out. It's kind of cool. And we actually published this work at Uppsala in 2014. Was the first thing we did on a generic, object-oriented, simple language. Right? We then went and got some great feedback from actually our product partners, and they said, this is kind of cool. This is neat. What would it actually look like if it were going to be useful to developers? Right? You can take snapshots. You can step back. And we actually talked with a bunch of developers, and they said, step back is nice, but I really care about reproducing the bug. So we learned a lot about, hey, here's a great idea, but our great idea didn't exactly solve developer problems initially. We needed to go talk with people and understand what problems they were trying to solve and figure out, okay, yeah, that's what we want to focus on, right? So this was great. I don't think it's just us taking ideas and throwing them to the product teams or our collaborators. It's also having this flow back about what is actually useful and what problems are worth solving and how do the things we're doing relate to those. So once we all agreed that, hey, we should be able to do this reproduction, the question was, well, your technique works great for a sort of simplified, perfect object-oriented language. That's not JavaScript, right? What are the things in JavaScript that would cause your technique to fail? Maybe you don't have to have solutions for all of these, but can you at least tell us where the danger points are so we can understand what risks we'd be taking on and what challenges will likely pop up as this project goes on. So we build some confidence with that, right? We then did some prototypes, proof of concepts, and everything was good. And now they've taken ownership of the code and they ship and iterate. But through this work, we've built a great relationship. So we go and we help them if they get stuck on something or they have some extra questions. And this also gives us a chance to continue having a dialogue with them and understanding where they see important trends going, like what is with the rise of sort of serverless or functions as a service, and what are the new challenges there that they know how to solve, and what are the new challenges there in the future that are looming that they don't know how to solve, that they would love some advanced thinking on. So for me, this was a great experience. This is why I wanted to go to Microsoft Research, to be able to do blue sky research, just think about some random things. And then also, when you see something that's exciting, go and actually get bits checked in and have them out there in the wild and get some feedback on them. So I don't want to sort of make this sound like it was a one-off, like I'm some magic guy and I'm the only person who knows how to collaborate with industry. So I want to point out a couple other projects. So there's IntelliCode, which is now a preview in VS, which is using some deep learning inspired solutions to provide some intelligence to the coding experience. Of course, Sumit Gulwani did a bunch of work in program synthesis, shipped his flash fill. Prose is his latest work there that's actually in a couple of products. There's some neural synth work, which is actually powering some IntelliCode stuff out of MSR Cambridge. Repeat is another time travel debugging experience that uses the Intel processor tracing functionality in the latest chips there to provide some sort of time travel debugging-like experiences in Watson Windows Crash Reporter. So this was also out of MSR Redmond. MSRD stands for Microsoft Security Risk Detection, which is the absolute most corporately named product I've ever heard of. But it's very cool. It provides fuzzing as a service for a bunch of third-party people, and it's based on a lot of the fuzzing work that came out of MSR Redmond as well. And of course, there's continued work in Z3, Lean, F-star, a lot of stuff I'm sure you're familiar with, and on and on. So I think this is great that there's all these projects that cover a full range of research to collaboration with the product group and wider collaboration with academia. So in conclusion, I have sort of two sets of conclusions. One, I want to say I think for a long time it was, you had a debugger, it was a GUI debugger, you could set watch points, you could inspect variables, and that's how you debug code. I think we can do a lot better than that. I think we can really revolutionize. There's going to be a sea change in the next 10 years about how people go about debugging and fixing bugs in software. I think time travel debugging is a key first part of that. Our key insight was, if you're in a managed environment, there's a lot of functionality that was built for efficient execution, but you can actually leverage that for gathering data and doing other analysis. So that's a great way to do it. Type safety and managed memory was what gave us these low cost snapshots. And then the second conclusion beyond just that work that we did on time travel debugging is, well, this is only the first step in this story, right? And it's enabling for doing this other work on automatic triage, program synthesis, risk estimation for new check-ins and all that sort of stuff. So I think it really opens up a great area of further investigation and development. As I said, our end goal, and one of the things I'm working on now, is how can we automate either all for simple bugs or part of and accelerate the process for more complex bugs through the observation, investigation, diagnostics, triage, repair, and final PRing. And then the other thing is, I think solving these problems requires both an investment in just the fundamental research, continuing ongoing, taking some of this research, understanding how it applies to our partners in sort of the industry or practice or whatever you want to call it. But I also think it's important to think about talking with these people and understanding what problems developers are actually facing and really learning from that. Like I showed this nice sort of, at least I think is nice, overview of how you actually go about diagnosing software. That was not at all how I thought about the problem before we started working with our product group partners, right? And the conversations that we were able to have with them, interviewing a bunch of developers, really was eye-opening to me to think about what challenges developers really face and where I wanted to go focus my sort of research efforts and where I wanted to try and think boldly about where the future went. And of course, maybe I have a bit of an advantage. Like, it's easy for me to walk across the street and go talk with people who are shipping software to millions and millions of people. But there's also great opportunities, like with the Node Diagnostics working group. They've been just amazing in their willingness to talk about their problems, excited about working with people in the industry. They've asked me, hey, can you point me to research on topic X? Because I just want to understand more about that. And I think great ideas can come from research. I'm willing to try and be bold. So, I think we should definitely take the opportunity to reach out to the open source community whenever we can, and really take advantage of that. So I have a bunch of links, Node Chakra Core, VS Code, TTD extensions, the Node Diagnostics working group GitHub repo where everybody posts issues. It's open to everybody. You can take a look and see what they care about. They have bi-weekly meetings. Anybody can phone in and hear what's going on. And just some info about Microsoft research and some of our outreach efforts at Splash this year. So I think I wanted to leave a good chunk of time for Q&A at the end. Hopefully I was successful in doing that.
So it's 2 minutes, so yeah, I think a question or two.
Okay.
Right, hang on. Right, here you go.
Hi Mark, great talk. I'm from MathWorks, and we try to do some of the similar things for MATLAB. MATLAB and JavaScript are similar in many ways, but we run into a couple of things in doing this for production environments, and I want to get your thoughts on it. One is one of the most useful places where people find debugging assistance useful is when they have a really long-running program, and it fails after having run for a day. And the problem with going the route of recording traces is it's prohibitive to record traces for a day.
Right, so this is why we want to do the snapshots as well. So by default, what we do is we have the system set up to record 2 to 3 snapshots every 2 seconds. And then once we have more snapshots than that, we just truncate the log and everything else. So we just sort of keep a ring buffer of the last 4 to 8 seconds of execution.
Yeah, which also limits how far back you can actually follow the chain of events in time.
Yes, so this is configurable. So if you wanted to record a minute, you can do that. But our feeling was that for the most part, if a bug takes more than, let's say 30 seconds from when the source is to when it manifests is, that's a pretty deep bug, and people are going to be dealing with shorter-lived bugs is going to be the majority of their time. But yeah, the ability to configure that and adjust some of these things is important.
And the question around similar lines is, people have found such tools useful when they're dealing with sporadics.
Yes.
But the very nature of sporadics is that they're caused by things outside of these like local variables and easily reachable pointers that you track. So they're caused by other system state which is very tangentially relevant. So you have ideas of how to augment your work to capture sporadics.
Yes, so I'm going to shamelessly plug. So I have a talk tomorrow at the Dynamic Language Symposium on logging, right? Because what we discovered a lot was when we go and talk with the developer, exactly as you say, a bug happens. They go investigate it. They don't want to immediately pull down a trace and get dropped into a debugger staring at a local variable, right? What they want to do is they want to go to their log, because that is their ground truth, about what is happening in the application. And they want to look at the log and say, oh, I logged that a network request failed, or a service went down, or what else was going on around this time. And sort of that helps them get this global picture that they can then take with them when they go debug. So I think this was one of the things I was alluding to. A challenge is I don't want to just have a trace. I want to gather all of this rich information and figure out how I can present it to a developer in a holistic way that helps answer their questions. And then again with this auto triage, if you have a bug, we would love to go back and say, oh, by the way, we looked at the last 5, just simple things. We looked at the last 5 PRs, and we reran your trace, deleting various parts of the PR, and now it succeeds. So maybe you should go look at that PR first, right? And that's a common debugging tactic. Or was there any other massive failure going on at that point in time? We should flag that for you and see if we sort of deleted that failure. Does that request succeed? So sort of doing a little hypothesis testing and helping point them maybe not at the true root cause, but at least giving them not just a stream of data, but helping them find insights that they can use to anchor themselves as they dive in and fix their bug. Yeah. So
Okay,
I totally agree with that. Thanks.
Right, so there you go.
Hi, thank you, great talk. It seems like you don't have to deal with issues related to parallelism and debugger implementation. So
That is one very nice feature of JavaScript. It's totally single-threaded. Yes.
So do you think how difficult would it be to extend it to handle languages, environments that actually are multi-threaded? This actually reminded me, like the code, sorry, reminded me very much of like the reactive libraries. Like especially on mobile, this is like pervasively used and it's super difficult to debug. So it would be great to have this kind of functionality where you could, basically retrieve past context from the point when you actually come to debug.
Yes. So there's one approach which is very common, and this is, I would call it uniprocessor multiplexing, right? So you can basically, if you're only running one thread at a time physically, you can treat the context switching as a non-deterministic behavior. And then you can just replay that thread order deterministically, and you'll have the replay debugging, right? So if your application is only using multi-threads because you just want to have a more fluid UI, this often works well. So Mozilla RR is a time travel debugger for Linux that does the full snapshot type thing, and it uses this approach. Like if you have a multi-threaded C process, it'll multiplex it to present only a single logical CPU core for the recording and replay phase.
So what you're saying is basically that the only thing you have to add is to record context switches.
Yes, and it has to be uniprocessor. Now this is fine for a certain class of tasks, but if you say, oh, I want to run ASP.NET, and it's assuming 16 threads, and I say you only use one, people are going to be very unhappy, right? So there's a variant that I find very interesting, which is sort of a deal. And it says, I tell you what, I will either, one, reproduce your bug perfectly, or two, I will reproduce a bug that is a true data race in your application perfectly, right? And if you make that deal, then we can do this for full multi-threaded as well, right? And that's one of the questions I've sort of been probing developers. What do they think of that deal, right? Do they want to be limited to one processor, or do they want to have a deal about they get one of two bugs? And I think that's, an interesting question about what is the use case they find most important.
So the corollary to that would be that if your programs are race-free, then approach number one would be sufficient. You might get multiple.
Oh, either approach would be sufficient, if you guaranteed your code was race-free, yeah.
Thank you very much.
Yeah.
So, any other questions? Right, here you go.
Say you have an application that calls down to some system C code from a custom binding. Is there a way to extend the time traveler debugger for that?
Yes, there is. So right now, there's a way to load arbitrary native modules into your Node application. We will successfully time travel debug the JavaScript interaction with all of those because they go across the host API. But it might not be very efficient if you're just doing a lot of busy calls back and forth with passive model binary. In theory, and this is something we'd like to investigate, but again, hasn't been a big enough pain point for us to really invest in yet, is you could change the recording API to go further down in these modules and record at a lower overhead and potentially even replay some of the native code behavior. But that's a little bit forward-looking, yes.
Right, so any other questions? Nope. Right then.
Well, thanks everybody for coming. I really appreciate it.